Hello and welcome to Algebra 2 Lesson 33. In this video, we're going to have a review of the rules of exponents. So I know for the majority of you, you thoroughly covered the rules of exponents when you were in your Algebra 1 course. Now we're about to start working with polynomials again, so it's very, very important that we understand the rules of exponents. So that's why we're going to review them in this lesson, and then in the next lesson, we'll start working with polynomials again. So the first rule I want to cover is the product rule for exponents. Super easy to remember. What it says is if you have like bases and you're multiplying, what you do is you keep the base the same and you add the exponents. So as an example, we have x to the power of a times x to the power of b. So the base is the same in each case. We have x and we have x. So what we do is we say this is equal to x, base stays the same, and we add the exponents. Exponent here is a, so I have a, plus the exponent here is b, so I have b. So x to the power of a plus b. And as an example of this, we have 2 cubed times 2 squared. So the base in each case is the same. It's a 2 here, and it's a 2 here. So I would keep 2 the same, and I would add the exponents. I would add 3 plus 2, which would give me 5, so this is 2 to the 5th power. Now, when we work with exponents, we can leave this as 2 to the 5th power because it's nice and convenient, or you could write 32. You can evaluate it if you want. Really, if you're in this section on your textbook, a lot of answers will be kept in that form. All right, so let's scroll down a little bit. For the next example, we see x to the 7th power times x squared. So the base x is the same, so I'll keep it the same, and I'll add the exponents. Here I have a 7, here I have a 2. So this would be x to the power of 7 plus 2, which is x to the power of 9. For the last example, I have 6x squared times 3x to the 4th power. So what I'm going to do is I'm going to write this as 6 times 3 times x squared times x to the 4th power. We know that 6 times 3 is 18. And then x squared times x to the 4th power, we have the same base, that's x. So we keep that the same. And we add the exponents. 2 plus 4 is 6. So this would be 18x to the 6th power. All right, so the next rule I want to deal with relates to the power of 0. So what happens when we raise a non-zero value to the power of 0? Well, it's 1, right? So if I have some x raised to the power of 0, as long as x is not equal to 0, the value is always going to be 1. So it doesn't matter what I plug in here for x, as long as it's not 0, and let me state that, we'll say x does not equal 0, then the value here is going to be a 1. So for example, 3 to the power of 0 is 1. This whole amount, 4x, or 4 times x, it's in parentheses, and it's raised to the power of 0. So this is 1. Then down here, let me kind of scroll down a little bit. We have negative 316,741 raised to the power of 0. Everything's in parentheses there, so this equals 1. So again, it doesn't matter what it is. It could be 1 billion. It could be 1 trillion. It could be whatever you want, as long as it's not 0. When the value is raised to the power of 0, it's equal to 1. So the next thing we want to talk about would be negative exponents. So what do we do when we run across these? So if I have x to the power of negative m, this is equal to 1 over x to the power of m. So basically what you're doing here is you're taking the reciprocal of the base and you're making the exponent positive. So the reciprocal of x would be 1 over x. So that's how we have 1 over x here. And the exponent goes from negative m to positive m. Another way you can kind of think about this, if I have x to the power of negative m, and I just write it over 1. If I drag something across the fraction bar, I just have to change the sign of the exponent. So if I drag this across the fraction bar here, what's going to happen is I'm going to have a 1 up here, and then down here, since I drag this down, I'd have x raised to, since this was negative, it will now be positive. So here's a perfect example of that. I have x to the power of negative m over y to the power of negative n. As I drag this across the fraction bar, you'll see here it's in the numerator. Y is the same, it's just that the exponent has changed its sign. It goes from negative to positive. Same thing here. X gets dragged across the fraction bar. It's now in the denominator. And notice how the sign on the exponent has changed. Here it's negative, here it's positive. So if you drag something across the fraction bar, right, from numerator to denominator or from denominator to numerator, you just need to change the sign of the exponent. So as an example with some numbers, let's say you had something like 6 to the power of negative 2, and this is over, let's say, 2 to the power of negative 3. What we can do is we can take this guy right here, we can bring it into the numerator. We just have to make the exponent positive. So this would be 2 cubed. And then we can take this guy right here, bring it into the denominator. We just have to make the exponent positive. So that would be 6 squared. You could verify that with a calculator. I can simplify this. 2 cubed is 8. 6 squared is 36. And we know they have a common factor. This would end up being 2 over 9 in its simplest form. And you can punch this up on a calculator and verify. You can do 6 to the power of negative 2 divided by 2 to the power of negative 3. Now you're going to end up with a decimal that's 0.2 with the 2 repeating forever and ever and ever. But it just verifies that you have the same answer here as the fraction 2/9. So I also have here 1 over x to the power of negative m is equal to x to the power of m. So if you have 1 over something where that something has a negative exponent, again, I can just drag this up into the numerator. I can think about this as being over 1, and I can change the sign of the exponent. Another way to think about this, kind of a longer way to think about this, if I have 1 over x to the power of negative m, remember, I could take the reciprocal of the base, make the exponent positive. So I could write this as 1 over x to the power of m. So if 1 is divided by this fraction, really I could write 1 over 1 divided by 1 over x to the power of m, which turns into 1 over 1 times the reciprocal of this, which would be x to the power of m over 1, which equals x to the power of m over 1, which is just x to the power of m. So that's how I got that kind of in a longer format. All right, so 2 quick examples. Let's say you see 6 to the power of negative 2. All this is it's 1 over 6 squared. Take the reciprocal of the base, make the exponent positive. The reciprocal of 6 is 1 over 6. If I make the exponent positive, instead of being negative 2, it's positive 2. You could leave it like this, or you could write 1 over 36. And again, another way to think about this, or an easier way to get the answer, is just to set up a little fraction bar here and say, okay, I'm going to drag this down here. I know there'll be a 1 up here now. And so if I drag this down here, 6 will be the same, but the sign of the exponent is going to be positive now. So this will be 1 over 6 squared. All right, then for the next example, we have 7 times x to the power of negative 4 over y squared. So again, with this part right here, I could separate this and say this is 7 over y squared times x to the power of negative 4. You can put it over 1 if you wanted to, it doesn't matter. If I take the reciprocal of this, what would that give me? So it would be 1 over x to the 4th power. So this would be 7 over y squared times 1 over x to the 4th power, which would be 7 over, you'd have y squared times x to the 4th power. Now another way to kind of think about this, and what I always do, if I have 7x to the power of negative 4 over y squared, you're just going to bring this down here. And again, when I cross the fraction bar, the exponent is going to be positive instead of negative. So I can erase this up here. And either way I do it, this is 7 over y squared times x to the 4th power. All right, the next rule, let's talk about the quotient rule for exponents. So if we have the same base and division is involved, we keep the base the same and we subtract exponents. So a to the power of m over a to the power of n is equal to a to the power of m minus n. Let's look at a couple of examples here. All right, for the first example, we have 6 cubed over 6 to the 4th power. So we have the same base here of 6. So what I'm going to do is keep that base the same, and I'm going to subtract exponents. Now to be more specific, I'm going to take the exponent in the numerator, which is 3, and I'm going to subtract away the exponent in the denominator, which is 4. Now 3 minus 4 is negative 1, so this will give me 6 to the power of negative 1, which we just learned as 1 over 6. All right, for the next one, I have 7x cubed over x squared. So I can write this as 7 times x cubed over x squared. And what we can do here, again, 7 just stays the same. That's unaffected. We have the same base, so x stays the same. And we subtract 3, the exponent of the numerator, minus 2, the exponent of the denominator. And I end up with x to the power of 1, or just x. So this would be 7x. All right, for the next problem, we have 6x to the 4th power, y to the 7th power, over 2x squared, y to the 8th power. So there's more things I can do here. I can cancel this 6 with this 2 and get a 3. That's how I'm going to start. Then I have x to the 4th power over x squared. So that's x to the power of 4 minus 2. Again, base stays the same. 4 is the exponent in the numerator. Subtract away the exponent in the denominator, which is 2. Then I have y to the power of 7 minus 8. Y and y, so y stays the same. The exponent in the numerator is a 7. Subtract away 8, which is the exponent in the denominator. So this gives me 3 times x to the power of what? 4 minus 2 is 2, so 3x squared. Then times y to the power of 7 minus 8 is negative 1. So I could rewrite this as 3x squared. I can drag y to the power of negative 1 into the denominator, and I would have y to the power of 1. Right? The y would stay the same, but the exponent will go from negative to positive because it crosses the fraction bar. All right, the next thing we want to think about will be some power rules. So we see something like a raised to the power of m. This is inside of parentheses, and it's raised to the power of n. This is equal to a to the power of m times n. So in other words, if I have a power already, and I raise that to another power, it's called the power to power rule, I keep the base the same, and I multiply exponents. So if I saw something like 2 cubed, and I squared this, 2 would stay the same, and I would multiply 3 times 2 to give me 6. So this would be 2 to the 6th power. You could prove that to yourself. 2 cubed is 8. If I had 8 and I squared it, I would get 64. Now 2 to the 6th power we know is 64. So either way, you can see that would be 64. Now as the next example, if we had a times b here, and this whole thing was raised to the power of m, I could say this is equal to a to the power of m times b to the power of m. So as an example of this, let's say we saw 2 times 3, and this was raised to the 3rd power, let's say. Well, I could say this is 2 cubed times 3 cubed. And you can prove this to yourself as well. 2 times 3 is 6. 6 cubed is 216. If I do it this way, 2 cubed is going to give me 8. 3 cubed is going to give me 27. If I multiply 8 times 27, I get 216 as well. All right, now we also want to look at, we have a quotient here, a over b. This is raised to the power of m. So we say this is equal to, we have a over m over b over m. So as an example of this, let's say I had something like 10 over 2, and this is squared. Well, this is 10 squared over 2 squared. Right? You can think about this as going here and also here. So this would be equal to what? 10 squared is 100 over 2 squared, which is 4. So this is 25. Now you can think about this another way. 10 over 2 is 5. 5 squared is 25. Now you might say, why would you do it this way? It seems like it's quicker with what you just did. Well, it's important to just understand that you can go back and forth. You might see something in this format and say, hey, it'd be pretty easy to do that calculation in this format. So you can go back and forth between the two. Okay, it doesn't matter. All right, so let's look at some examples. If I have 6 cubed and then it's squared, it's again that power to power rule. So 6 stays the same, and I would multiply exponents. 3 times 2 is 6, so this would be 6 to the 6th power. For this one, I have 2 to the power of negative 1 times x to the 4th power, and this whole thing is raised to the power of negative 2. So again, the base in each case would stay the same. So 2 stays the same, and you'd have negative 1 times negative 2, which is 2. Here I'd have x to the 4th power, so x stays the same, and we do 4 times negative 2, which is negative 8. So the base stays the same, and you multiply the exponents. Now in this case, since we know that x to the power of negative 8 is 1 over x to the 8th power, I can just simply write this as 2 squared over x to the 8th power. Remember, if I grab this right here and I bring it across the fraction line, what I know is x stays the same. The exponent goes from negative to positive. All right, the next one we're going to look at, we have 4 times 3, and this is all raised to the power of 2, or you could say it's squared. So this is the same as saying we have 4 squared times 3 squared. Now let's look at the next one. All right, for the next one, we have 6xy inside of parentheses. This is raised to the power of negative 4. So I could do this a few different ways. The first way I could do it is I could just take the reciprocal of this guy right here, and I could raise it to a positive 4. So I can say this is 1 over, and then I'll have 6xy, this in parentheses raised to the power of 4. Then I would use my power to power rule. Remember, everything has an exponent of 1 right now. So 4 times 1 would be 4 in each case. So everywhere we'd have 6 to the 4th power, x to the 4th power, y to the 4th power. So everything would have an exponent of 4. Now, another way you could have thought about that, let's just erase this real quick. We could say, okay, every exponent here is a 1 inside the parentheses. So I'm just going to say, okay, 6 to the power of 1 is raised to the power of negative 4. So that would be 1 times negative 4, or negative 4. So I'd have 6 to the power of negative 4. Same thing for x. I'd have x to the power of negative 4. Same thing for y. I'd have y to the power of negative 4. Then because these are all negative exponents, I can drag everything across the fraction bar, make the exponents positive. So I can have 6 to the power of positive 4, x to the power of positive 4, then y to the power of positive 4. Again, I move these from the numerator to the denominator. So I have 1 over 6 to the 4th power, x to the 4th power, y to the 4th power. What about this one? We have 10 over 5, and this amount is squared. So I can write this as 10 squared over 5 squared. And again, you can prove that to yourself pretty easily. 10 squared is 100, 5 squared is 25. The result of this would be 100 over 25, which is 4. If I did it in here, 10 divided by 5 would be 2. Then if I square 2, I get 4. So either way, it's the same. All right, then lastly, I have x to the power of negative 1 times y. This is over z cubed. And then this is inside of brackets, and it's raised to the power of negative 2. So you can think about each base here as staying the same and just multiplying the exponents. So x stays the same. Negative 1 times negative 2 is 2. Y stays the same. Remember, it has an understood exponent of 1. So 1 times negative 2 would be negative 2. This is over. We have z, which stays the same. 3 times negative 2 is negative 6. So now all I want to do, x squared would stay the same. This would go into the denominator, and so I would change the sign of the exponent. So it would be y squared. This would go into the numerator, so I'd change the sign of the exponent. It would be z to the 6th power. So x squared times z to the 6th power over y squared. All right, so let's look at a few practice problems before we kind of move on to our topic of polynomials. So we have 2a to the power of negative 1 times b to the power of 0, and this is over. We have a to the power of negative 5, and this is raised to the power of negative 5, times negative 2a to the power of negative 4, times b squared times a squared. So if I simplify in the numerator first, I know b to the power of 0 is 1. So I can kind of cross this out and just put a 1 there. 1 times anything is just itself. So the numerator I'm going to write as 2a to the power of negative 1. For my denominator, I got a lot of stuff going on. So I've got a to the power of negative 5 raised to the power of negative 5. So a stays the same. Negative 5 times negative 5 is 25. Then times, you have a negative 2, a to the power of negative 4, b squared, a squared. So let me write 2a to the power of negative 1 over. I have a to the power of 25, I have a to the power of negative 4, and I have a squared. So keep a the same and just add those exponents. 25 plus negative 4 is 21. 21 plus 2 is 23. So I'll have a to the power of 23 there. And I have that negative 2. Now what I can do is I can cancel this 2 with a negative 2, and I can put a negative 1 there. So instead of having a 2 there, let me just put a negative in front of that a to the power of negative 1. All right, so now The next thing I have is a b squared. Nothing I can really do with that, so I'll just rewrite b squared. So the last thing is, let me write equals. I'm going to put a -1 times. I have a to the power of -1. Now I have an a to the power of 23 here. So what I can do is keep a the same. I would subtract -1 minus, we have 23 in the denominator, so minus 23. And this would be over b squared. So again, I'll have -1 times. We'd have a to the power of -1 minus 23, which would be -24. This is over b squared. The last thing I'm going to do is I'm going to put this in the denominator. And when I do that, I'll have -1 over b squared times, this a will be the same, but the exponent, because I'm dragging it into the denominator, will be positive. So a to the power of 24. So -1 over b squared times a to the power of 24. All right, for the next one, we have -2x to the power of -3, y to the power of 6. This is inside of parentheses and it's all squared. Then this is over. We have -2y squared times -x to the power of -2 times y to the 6th power. So let me start out in the numerator here. Just think about, this is going to be applied to everything. All right, that's your power to power rule. Now, I want you to be very, very careful here. This -2 is inside of parentheses. It's inside of these parentheses here. So that negative and that 2 are both squared. So I could do this two ways. I could say I have -2 like this squared, or I could treat this negative as a -1 and say that's squared, then times 2 squared, then times x to the power of -3 squared, then times y to the 6th power squared. And if I go through on each thing, -1 squared is 1. So this is 1. 2 squared, I'm just going to leave it like that for now. X to the power of -3 squared would be x to the power of -6. And then y to the 6th power raised to the 2nd power, or y to the 6th power squared, would be y to the 12th power. Then this is over. I have a -2, which I'm going to write as -1 times 2. Then I have y squared. Then I have a -x. So I'm going to write -1 times x. This is raised to the power of -2. Then times y to the 6th power. So a lot of things we can do. And I want to go slowly. I know a lot of you can do this much quicker, but I want to go slowly so everybody can follow along. So let me just start by simplifying in the denominator real quick. So in the numerator, I'm going to leave this as 2 squared times x to the power of -6 times y to the 12th power. In the denominator, I'm going to leave -1 times 2. What I'm going to do is I'm going to say I have y squared times y to the 6th power. Y stays the same. 2 plus 6 is 8. Then I have times another -1. So -1 times -1 is 1. So we can erase both of these, okay? And I'll just slide this down. And the next thing I see is times x to the power of -2. So what I know is, if I have the same base here, I have 2 squared and I have 2 down here. You think about this as 2 to the 1st power. This is going to tell me I have 2 to the power of what? Subtract exponents. You'd have 2 minus 1, or 2 to the power of 1. Then next, I have x to the power of -6. And I'd subtract away a -2, because I have x to the power of -2 down here. Again, this seems a little weird, but if I have a -6 here, that's what I start out with. I'm subtracting away a -2. Minus a negative is plus a positive, so -6 plus 2. So -6 plus 2 is -4, so this would be x to the power of -4. Then lastly, I have y to the power of 12 here, y to the power of 8 here, so this would be y to the power of 12 minus 8, or y to the 4th power. So if I wrote this over 1, I could drag this down here and say this is what? This is x to the power of 4. X stays the same. The exponent's sign is going to change. So I can just erase this and say we have 2y to the 4th power over x to the 4th power. All right, so for the last example, we have 2x to the power of 0, y to the 4th, z to the 7th, times 2zy to the 5th, over 2x to the 8th power, y to the 7th, z to the 8th. Everything's inside of brackets and raised to the 6th power. So that means that every item inside here is raised to the 6th power. So 2 is raised to the 6th power, x to the power of 0 is raised to the 6th power, y to the 4th is raised to the 6th power, so on and so forth. Now, you could go through and do that now, but it's going to be easier if you simplify what's inside the brackets first. So let's do that, and let's do it in a quick manner. So I'm going to start out with 2. I have a 2 here and a 2 here. So same base, I would add the exponents. So this is a 1 and a 1, right? The exponent's understood to be 1 there. So that would be 2 to the power of 1 plus 1, which is 2 squared. Now I also have a 2 in the denominator. So if I had 2 squared over 2, the exponent down here is a 1 as well. That would be 2 to the power of 2 minus 1. And so this would be 2 to the power of 1. The next thing I come across is x. So here I have x to the power of 0, which is 1. And down here I have x to the power of 8. So I'm just going to leave that x to the power of 8 down there. Then next I come across a y. So y to the 4th power, I have a y to the 5th power here. So again, if I did my product rule for exponents, y stays the same. I'd add 4 plus 5, that would give me 9. But then I have a y to the 7th power in the denominator. So for that, use the quotient rule for exponents. Y stays the same. I would do 9 minus 7, which would give me 2. Then the next thing I come across is z. So I have z to the 7th power here. I have a z here. So the product rule for exponents tells me that z stays the same. 7 plus 1 would be 8. Then down here I have z to the 8th power. So what would happen is I would have z to the 8th power over z to the 8th power, which is 1, right? Or you can think about it this way. I would take the exponent in the numerator, which is 8, subtract away the exponent in the denominator for z, which is 8. That would be z to the power of 0, which is 1. You can get rid of z. All right, so we've dealt with all of that. So don't forget your brackets here. And this is all raised to the 6th power. So 2 to the 1st power is raised to the 6th power. 2 stays the same. Multiply 1 times 6, you get 6. Y squared is raised to the 6th power. Y stays the same. 2 times 6 is 12. So that's y to the 12th over. X to the 8th is raised to the 6th power. X stays the same. 8 times 6 is 48. So we get 2 to the 6th power times y to the 12th power over x to the 48th power.